my wardrobe is kind of limited. But I try to make them appropriate to the talk, so this is my impression of a black hole. It's all improvement from here on. Take two. Our speaker tonight is one of the world's leading astrophysicists, and she says that these decades are a golden age of cosmology. And by that, she means that the really profound mysteries are turning up, and the questions are coming faster than the answers. And she's in the thick of finding the answers. Priya Natarajan.
Okay, first of all, it's a real honor and a privilege to have the opportunity to talk to you all today. And what I am hoping to do in my talk this evening is to try and give you, in some sense, a status report of what we know about the key ingredients of our universe. So one of the reasons I'm sort of giving you this preamble, you might have already guessed, is that we simultaneously know quite a lot and not a lot. And this is a situation that, as scientists, we have to constantly live with. And it's part of the exciting enterprise of doing science, the practice of science, that the minute you have a really good, well-formed theory, we're on our way to try and disrupt it, to use a Silicon Valley term. We want to actually change it. We want new evidence that would possibly invalidate it. So we are sort of constantly moving the bar in trying to understand quantities that have been very hard to figure out. And the minute we do, we want to sort of get rid of them and try to see if something new, something better, something that's a better description, that has more explanatory power, can replace that. So I'm hoping to show you some of that process as well, because that is what the day-to-day work of a scientist like me. And often people ask me when I'm sitting in my office, I'm often just sitting and staring into space, actually, and I'm waiting for that window of inspiration where something will kind of click, and you never know when it's going to come. And so my students walk past and they say, okay, she doesn't seem busy, but then they're really scared and they come in and I say, oh yeah, I am actually busy. They're okay. So I'm hoping to sort of convey some of the excitement of what we actually do. So the essential is invisible to the eyes, says the fox in The Little Prince. It's one of my favorite stories. And so the human imagination, right, we've always been fascinated with the invisible and the unseen entities. So earlier on in the medieval ages, it was ether, it was miasma, it was phlogiston, and these were all shown to be non-existent. But wait, so are we done with invisible forces in the universe? So it turns out, nope. In fact, more than ever, our worldview and our understanding of the cosmos hinges on unseen quantities. And I'm going to try to show you that these are different. These entities, dark matter and dark energy, are not going to go the way of ether. Okay? We don't think so because we have a lot of independent lines of evidence that suggests that they are real. Of course, one is always open to surprises, and nature might quite surprise us, and we may be able to have a breakthrough that disrupts this entire notion of definition of dark matter, and maybe there's a new theory that doesn't need these ingredients and needs something else. So let me, first, before I move on, the work that I have been doing and the work that a lot of us scientists have been doing is never done alone, right? This trope of this single scientist with unkempt hair thinking great thoughts. It doesn't work anymore. We all work in collaborations, and I just wanted to acknowledge a lot of the people, many of my students and postdocs who over the years have contributed to a lot of the results that I'm going to show you here, my results, some of my results that I'm going to show. I'm going to give you, paint a broader picture than just what I do. And there are many of them are former and current students at Yale, former postdocs. And I've also been very fortunate to have gotten funding from NASA and NSF and the Guggenheim Foundation and so on, so I'd like to acknowledge that. Okay, so before I go on to tell you what is peculiar about the dark components in our universe, let me just first, before I disorient you and tell you, let me give you the sort of the comforting idea first, which is that we have a really good sense at the moment of cosmic history. We have a really nice story that is backed up by evidence, and some of it incontrovertible evidence. And essentially what we now know is that our universe is roughly 13.8 billion years old, and it started off very early on, set off by what is a misnomer, a Big Bang. It was not really an explosion, but it started off where we define t equals 0, start of time. There was a brief period of exponential expansion, the inflationary era, and then after that we had an epoch when the universe, the energy of the universe was dominated by radiation that we now see as the cosmic microwave background. And then there was an epoch where matter started to dominate the inventory of the universe and drive its fate. And then today, more recently, we find that the fate of the universe is driven by dark energy, this unseen mysterious force that we'll be talking about. Now, these two components, so much of the matter in the universe is dark matter. So the majority, more than 90% of the matter constituents of the universe are dark matter. And what is special about dark matter is that it does not couple to any radiation. So you see no photons in any wavelength coming from any interaction with a dark matter particle. It likely very weakly couples to stuff, to itself. We don't know at the moment. And it's not made of ordinary atoms. So this is stuff that is not on the periodic table. This is not stuff that was synthesized in the centers of stars, as far as we know. This was just some exotic particle that was formed very early in the universe. The interesting thing, as I will show you today, is we know a lot of things about dark matter quite exquisitely. How it's spatially distributed, for example, but how it aggregates, how it evolves over time, how it shapes the entire universe. In fact, it shapes the entire universe. But we don't know what that particle is. And that's what is very troubling about the problem. I mean, we are making progress, and I think I'll show you what the latest is on. So the only thing that we do know about dark matter is that these particles have mass, and therefore they have gravity. And it's the gravitational effect that dark matter exerts on particles that we can actually see radiation from in its vicinity that have given us the clue to the existence of dark matter. So I'll spend some more time, I sort of lay out the land of how we've actually discovered dark matter and dark energy. And so the two ways in which dark matter has revealed itself is by the dynamical effect that it has on stars and other galaxies in the universe. And the other way in which we have found dark matter is the fact that matter bends light. And so by the bending of light light is our sort of photons are our cosmic messenger. Everything we know about the universe has come really from photons. And dark matter, all matter in fact, has a very profound effect on the paths of photons in the universe, as we will just see. So these are sort of the two independent lines of evidence. And it turns out that even dark energy, it's the same. I mean, because dark energy, as we will just see, is a mysterious force, a repulsive force that counteracts gravity that is accelerating the expansion rate of the universe today. And its effects are found not by the effect it has on individual galaxies or individual stars, the motions of individual stars, but the motion of the entire universe, right? So it's a sort of a scaled up, if you will, abstract and more powerful force in some ways. Definitely more mysterious at the moment. But before I proceed, there are a couple of preliminaries that might be useful to cover so that the kinds of evidence that I'm going to be summoning to show you that dark matter is real. So, for example, we can focus on, as I said, light is the cosmic messenger. And the couple of properties of the transmission of light in the universe that are sort of relevant to our understanding of dark matter is the fact that when we look out into the night sky, and I find this fact still quite incredible and awe-making, that when you look out into the night sky with the largest telescopes that we have on Earth, we're actually looking back in time. So the deeper we look, the farther back in time we can access, right? And the universe is expanding at a pretty fast clip today, right? And as I just mentioned, dark energy appears to be the energy that is powering this expansion. Now, any expansion of the universe will stretch wavelengths of light. And so the graphic here, suppose our universe was, the space in our universe approximates, say, the outside of a sphere. I'm not saying that that's what our universe is, but an example, a nice visualization, is then you can see that as the sphere expands and you are seeing the paths of photons, these wavelengths that are shown here, they get stretched out. And what we really measure from the stretching out of this wavelength, which is called redshift, we can actually measure distances, and we can actually measure even the expansion history of the universe itself by looking at this. So for example, when we look back in time, we can look at the spectrum, the energy that's coming from the sum of all the stars in a galaxy. We can look at the spectrum that is of a galaxy that's nearby versus one that's farther away, and we can actually calibrate where they are by looking at the stretching of the fingerprints of the atoms that we actually know. So thankfully for us in the universe, physical laws are invariant. So a hydrogen atom here and the energy transition levels that you have on Earth are the same on Andromeda or any other distant galaxy, thankfully for us, right? And so because we have that calibration, when we see the stretched wavelengths, we can kind of figure out how far an object is and how fast it's moving away from us. And so these spectra, which are for distant galaxies that we can measure, so you can measure both the expansion of the universe and any systemic local motions that they have. Both of these can be sort of disentangled and measured compared to a nearby standard. And so this is a sort of key in terms of how these measurements are made, right? So it's actually a lot of it is from spectra. Anyway, so Newton did something quite remarkable when he was able to connect the celestial and the terrestrial, which is with his universal theory of gravitation. So he conceived of gravity. What he came up with is how gravity acts. What he didn't come up with is what gravity is, right? But he gave us a really nice explanation for how gravity works. So you have a body of mass m1, another body of mass m2, separated by some distance d, and the force of gravity exerted by one on the other is proportional to the product of the masses over the distance square, right? So the ancients, right, were looking for patterns on the sky, and they were not looking for an explanation. The reason this was remarkable was that it was after Brahe and Kepler onwards that we've been looking at the night sky, not discerning just patterns, but wanting an explanation. So Kepler and Brahe put us on this track of trying to find an explanation. And Newton came up with this incredible operational description for gravity, and he ruled for 200 years. And then Einstein came along and upended him. Einstein came up with a fundamental, it was not an incremental sophistication, a slight refinement in Newton's theory. This was a fundamental reshaping, a fundamental reconceptualizing of the cosmos. In fact, the entire cosmos. So the general theory of relativity that he published in 1916, it is actually applicable to all kinds, all scales, all astronomical scales, gravitating systems, black holes, planetary systems, in fact, the entire universe. And that was what was audacious about it. That this was one theory that actually in which, and I will show you the equation. I think this crowd might actually like that equation. It's a beautiful, compact equation to have the audacity to think that you could actually write quantities pertinent to the entire universe on the right-hand side and the entire universe on the left-hand side and say that they could be equal. I mean, that was what was remarkable. And the profound connection underlying all of this was a profound connection between mass and space. So in Einstein's version of gravity, so Einstein actually came up with an explanation for gravity. And his explanation was the presence of mass creates curvature in space-time. So he conceived of space as a four-dimensional entity. And because he realized cosmic scales, in order to describe an event that occurs at any point, you need to specify not just where it happened, but when it happened, because the speed of light, although large, is finite. And in order to uniquely pin when events happen, you need to know all four coordinates. So this led to this sort of geometric conception of this entity called space-time. And the sort of cliched way of saying that is space curvature tells masses how to move, and mass creates curvature in space. So it is curvatures in space-time that actually causes masses to move, right? And space-time is where we live. Everything in the universe is space-time. There's nothing above space-time. There's nothing below space-time. Therefore, if we are thinking of photons or light rays traveling in the universe, they are confined to space-time. So one of the key breakthroughs with Einstein's thinking was the way in which he was able to link with his field equations the contents, the geometry, and the fate, the evolution over time of the entire universe. So I should quickly point out here that Einstein was actually not very happy with an expanding universe. He really liked the static universe of the ancients, and he tried really hard to keep the universe static, even though there was overwhelming evidence, as I'll just show, from Hubble, from data, empirical evidence. He couldn't dispute it. And it took him a long time to actually sort of let go and say, okay, I can live with a universe that is expanding. So Einstein's theory of general relativity, now we see that it explains not just our cosmic inventory, dark matter and dark energy, but it also tells us that there is a fundamental link between the geometry of space-time and the contents and the measurable expansion history of the universe. It's an observable quantity. It's something that you can measure. And you can also measure the contents of the universe. The inventory of the universe can be taken. So if you do those things, so of these three quantities, if you know two, you can actually determine what the geometry is, for example, right? Now, the evidence for dark matter hinges from the application of this version of gravity. The need for dark matter arises even if we think of gravity a la Newton. But the compelling evidence comes from the general theory of relativity, because it allows us to actually measure and relate these three quantities. As I said, they're all empirically measurable quantities. So today, what I'm going to focus on in terms of cosmic objects that are going to help us understand the nature of dark matter and dark energy are these objects called clusters of galaxies. And they're the most massive assembled structures in the universe. They have a total mass, which is in excess of 10 to the 15 times the mass of the sun. And I particularly like these objects because they can help us measure both dark matter and dark energy. So although the measurement of dark energy, the discovery of dark energy, did not happen with clusters of galaxies. The objects that were used to discover them are supernovae, and in the audience today we have the guru of the field, Bob Kirshner. Supernovae, a standard class of supernovae that are like standard light bulbs, were used to actually measure the geometry of the universe, and that's how dark energy was discovered. However, today I'll be focusing on a different and a new way, a slightly more challenging way. But in my opinion, it's sort of rich rewards because you kind of get, two things for the price of one. You can actually get a dark matter and dark energy simultaneously. It's of course, therefore, complicated, but if we can do it. So just to get back to this notion of space-time, as I said, it's a four-dimensional sheet, four-dimensional entity. You have three space coordinates in one time. And just to show you the effect of masses on space-time. So if you have an object, so flat space, no mass, no undulations, no divots, no potholes. If you have the sun, you see this sort of curve in space-time. And if you have an object that's more dense, like a neutron star, notice that the curvature is stronger. And then, of course, you have these enigmatic objects in the universe, very, very compact black holes. They're actually a puncture in space-time. So this is the effect in terms of what mass is doing to space-time. And so these are Einstein's equations. And I just could not resist putting them on a slide for you. So just to show you that these quantities, it's a beautiful shorthand for a very large number, 10 equations. And so what it's showing you is this g mu nu term. That's the curvature. That's the shape of space. This t mu nu is the mass energy content of the universe. And then this other peculiar term is the vacuum energy of the universe. This is sort of the ground state energy of space-time itself, if you will. And so the properties of the universe, space-time, and we're going to be looking in the context of this sort of shape of space, mass, and what mass does to space, the propagation of light in the universe, what the implications are for light propagation in the universe, because light is really the messenger of all measurements are made with light, really. And of course, this equation also predicts the existence of black holes and gravitational waves. And you might have all seen the recent excitement that black holes finally became real. We saw the direct detection of gravitational waves from emerging black holes that have revealed that these entities exist, right? Because the black hole solution. So the solutions to this equation, right? So the black hole solution is one exact solution to this equation. It describes the space-time geometry around a very, very compact object. So another set of solutions to this equation actually describe the entire universe and its expansion history and its contents. And that actually comes out of these. This is the last set of equations before you all say, oh my God, okay. So it comes out of these two equations. And one of the sort of key assumptions to get, this is an exact solution. So what's really interesting is Einstein never thought that there would be exact solutions to these equations. He said, there'll be some approximate solutions. And so when these solutions were found by Alexander Friedman, he didn't like them. Well, he didn't like them because the universe was not static, right? These were sort of time-evolving equations, which he was not happy about. But he came around to it. He tried very hard to make them static, and the way in which he made them static is by adding this lambda term that I showed you in the field equations as well. So these two terms is what Einstein added in. So they sort of mimicked some kind of repulsive force that would counterbalance gravity and then keep the universe static. And it turns out we've kind of come full circle in terms of how we interpret that quantity. So just to give you a feel for the solutions for the expanding universe, so we have the cosmological principle is sort of an underlying ansatz, right? So that's our baseline, which is we see what every other observer. So no observer is unique in the universe. There's no particular special vantage point. So we all see the same stuff. And so for homogeneous and isotropic universes, the expansion and contraction, you can have both expansion and contraction mathematically in the solutions, right? The question is, you have this set of solutions, which one best describes our universe, right? The one that we live in. And the way to think about these solutions of expansion and contraction is to sort of intuitively, you can see, right? Gravity is attractive. It would tend to kind of pull things together. And if you want to be GR savvy, it creates these potholes, and therefore masses will feel the curvature and move accordingly, right? Whereas if you have a repulsive force, you tend to stretch out space-time. Instead of causing a divot, you actually stretch it out. So in a way, the solutions that give you expansion and contraction can be sort of attributed to the sort of the tussle between these two forces. So in 1929 to 1935, Edwin Hubble discovered that galaxies, bar one, every other galaxy in our vicinity. Well, of course, he first figured out that there were other external galaxies. Even that was not known, right? At the time, it was believed that we were alone, and this was this one galaxy is all there was in the universe. But he realized, well, he found, more than realized, it's empirical data. This is not a very convincing straight line, but there was a leap of faith, and the points filled in. But I wanted to show you the first plot that he published. So he noticed that the velocity with which galaxies were receding away from us was directly proportional to their distance from us. So that's the velocity v, and that's the distance r, and this h is called the Hubble Constant. So to give you a better sense of what it really means to talk about expanding space, because this is going to underlie, all the measurements that I'm going to talk about that give you evidence for dark matter and dark energy. So when space expands, it's like having a grid, and the entire grid expands. So you're not expanding into something, and that's a very common misconception. So the entire grid kind of expands. And remember, the grid is everything. There's nothing above, there's nothing below. So, it's a four-dimensional manifold. Okay, so there are three distinct solutions, three distinct possibilities for universes, three combinations of fate, geometry, and contents for the universe. And they're encapsulated here in terms of the expansion scale of the universe, how the expansion rate changes over cosmic time. So you have these three possibilities, there are three solutions. And again, the quest of observational cosmology is to try and figure out which one we are on, which one is our universe on, right? And of course, there's also correspondingly three different options for the geometry of the universe, right? So one is the outside of a sphere, the other is my favorite, which is Pringle chip, the saddle. It's a favorite because of my fondness for Pringle chips, not because the universe is actually a saddle. And the other, of course, is a flat geometry. So, these are sort of very simple kind of notions that we can understand, where essentially, how do you discriminate these, right? I mean, the whole idea is we want observations to be able to discriminate which of these solutions we're on. So how do you discriminate this? You can see, for example, if you're on the outside of a sphere, the sum of the angles of a triangle are not going to add up to 180 degrees. So if you can kind of make some measurements, you can figure out what kind of surface corresponds to the surface that best describes our universe. So now we actually have a full inventory of the universe, and this is where the bizarreness starts, okay? So we look at, the ordinary atoms that we're made of, all the stuff in the periodic table, the stuff that was synthesized in the first 3 minutes of the universe that is up to lithium-7, and then everything else that was synthesized in the periodic table in the centers of stars, all this sort of romantic stuff of we are made of stardust. Yes, that's awesome, but we're only 4.6%. Of this whole, of this inventory. 23% and more than 90% of the matter piece is actually dark matter, which I told you does not have any radiation, does not emit, it only has gravity, and we don't know what the particle is, right? And the rest, the 72% in blue, is dark energy. This is the force, the mysterious force that is pulling everything apart and causing the accelerating expansion of the universe. Now, one of the interesting things is, remember, I've been talking about the universe and the solutions not being static, right? They're evolving in time. So if you look, when the universe was about roughly 400,000 years old, so we now have data from which we can infer what the components were, how much they contributed at that time. And we actually now know that at the time, the inventory was slightly different. Dark energy was not very consequential at that time. It hadn't come into play, right? It kind of kicks into gear very late in the universe, okay? So this was the sort of the discovery of dark energy, the plot that shows so the way dark energy was discovered, as I said, you have these standard light bulbs, these type 1a supernovae that are very bright and therefore can be spotted out to great distances in the universe. And we know they're standard light bulbs, give or take. There's a little bit of, further physics that needs to go in to standardize them and to understand some of the systematics. But essentially, the idea is that it was found that supernovae were fainter than our expectation if The only thing that would be causing the dimming was the 1/r² fall off with distance. And people tried to explain this away. Maybe there's dust, maybe there's something else going on. So it turns out that 2 independent teams around the world discovered, they had a few supernovae in common, but not very many. They even had completely different supernovae, different data from 2 different hemispheres, and they arrived at the same conclusion. And this very bizarre conclusion, very uncomfortable conclusion, which I think we, again, rapidly accepted scientifically, right? There was not as much pushback. Why? Because there were 2 independent teams with very compelling evidence, right? And they did not share methods or analysis or whatever. It's completely independent, and they arrived at the same conclusion. And so, and I think this is remarkable. This is one of the most remarkable recent discoveries that has reshaped our view of the cosmos. It's radical. And as I've told you, we don't know what dark energy is, right? This is empirical evidence that there's something going on that is causing the accelerating expansion of the universe. So we don't actually know if there is a field at some point that kicks into gear, that moves, changes the inventory, suddenly starts to become important. We roughly know when it starts to kick into gear, but we don't actually know why and how, and we don't know if it'll go on forever, will it stop, et cetera, et cetera. Okay, so it's a remarkable discovery. And it has implications. It has very, very significant implications for our cosmic future, as well as it tells us something quite specific about our past. And that inventory that I showed you when I first started, and I said, okay, here's the comfortable part of the story. So it actually describes the solution that best matches our universe is one in which the universe is rapidly accelerating today. It was radiation dominated earlier, dominated by dark matter after that, and then dark energy takes over. So we know that that's the universe we are living in. And for the far future, there are very interesting implications, right? So the universe is going to get lonelier and lonelier because the accelerating expansion, our nearby galaxies are going to be further and further out. So it's going to become a more desolate place. I mean, we're talking billions and billions of years. So, it's not anytime soon. But one of the advantages of working in cosmology is that somehow when people tell you, oh, I'll see you in 15 minutes, and you're like, yeah, okay, that's nothing, right? Because I think in mega years, or I think in millions of years, or billions of years, yeah, sure. So one has to recalibrate. I find that I often have to kind of recalibrate sort of reality and sort of say, okay. And someone will ask me, so how quickly do 2 galaxies merge in the universe? This is sort of suppose there's a new image. And I'll say, oh, that's going to be very rapid. It's just 5 million years. And So I think cosmic scales are incredible, and I think they're actually very humbling because we live in this sort of Anthropocene period where everything revolves around us, and you suddenly realize that our lifespan is not even a blip, right? It's not even a blip. But we are very consequential because we have the cognitive capacity to have figured all of this out, right? That is incredible. Okay, so this is coming back. So this is what our current cosmic picture is. That there was some early, so there are lots of gaps. We don't know a lot of things. I'm sweeping over many things that we don't know as well. But we know where we stand with the data. So let me just now dive right into the evidence for dark matter. So the evidence for dark matter that I'm going to show you is going to be from the impact that dark matter has on dynamics, the motions of stars, so gravitational impact, and the impact on the bending of light rays. And similarly, the evidence for dark energy that I'm going to show you, because I'm going to be looking at this particular set of objects called clusters of galaxies, again, its impact on dynamics now of the entire universe. It's not individual objects, but the entire, so it's sort of an expansion of scale. And it's, of course, the impact on the bending of light rays as well. Okay, so what is the compelling evidence? So if you look at the solar system and you look at gravity in the solar system, you see that the speeds, and you plot up the speeds of planets around the sun, you see it's a nice declining graph. Saturn is moving much slower than Venus is, and so on and so forth. And this is because the major gravitating body in the solar system is the sun, and it's lying at the center. And as you fall off, it's a pretty good Newtonian 1/r² kind of description, right? So Newton is good enough for this sort of broad brush picture. And so what you expect, so this thing is called a rotation curve, so it's just a fancy way to say velocity is a function of distance, and it's declining, okay, as we go further away from the sun. So the question is, if you go out and do the same measurement for a galaxy, and now you measure the speeds of stars away from the center of a galaxy, what do you see? It turns out, so this is the top view of a galaxy, a real galaxy, for which such a measurement was made. So as a function of radius, you're looking at the speeds of stars. This is a spiral galaxy. And what do you see? You actually see this. Okay, completely counterintuitive, completely different. So Vera Rubin and Kent Ford in the 1970s actually made these measurements for many spiral galaxies, and actually they sat on the data because they were a little uncomfortable with the interpretation of what this meant. Because this is suggestive that there is something that is distributed throughout the galaxy that beyond the visible stars, beyond the mass and visible stars. Because you see the stars, you can weigh them, and you can figure out how much they weigh, and so there's some other gravitating component that is holding up the stars in the galaxy, right? And so it turns out that this is dark matter, and it's not just a one-hit wonder, you see it in most galaxies. So it's not like there's one peculiar class of galaxy where you see it and you don't see it everywhere. So it's generic, you see it everywhere. Pretty much every galaxy, there is very strong evidence that galaxies are a huge repository of dark matter. So I just want to show you some of the real data. So this is from the original paper in 1978, which they finally published. And you could see that they had these curves going out to quite far away. In fact, they were starting to probe distances away from the center where they run out of stars, but you see gas. So the gas motions also reflect the gravity of whatever is there that's holding the system together. And they found that the rotation curves were flat. And the only explanation for that is that you have some gravitating mass all the way out. And so this is our current sophisticated conception of a galaxy. So we think that every galaxy, what we really end up seeing is a very small percent of its mass, which is visible stars in the center. And everything else, you have a very extended distribution of dark matter. You have a halo. And you may ask, does the halo actually stop? It turns out that it doesn't quite stop. It kind of oozes cosmically. So there isn't like a sharp edge. But this is a sophisticated cartoon. Okay, so let me quickly move on to the other line of evidence that I'm going to show you for both dark matter and dark energy. And general relativity celebrated the centennial last year, and this the celebration of this whole set of equations that have transformed our cosmic view. And one consequence, because of the potholes in space-time that are now going to be created by the existence or presence of masses, photons or light that travels to us from any point in the universe to us will actually track and follow every divot, every pothole as it reaches us, right? Because remember, the space-time is everything. There's nothing above. It can't fly. There's nothing above or below. Our universe is space-time. And so Einstein was actually able to calculate that in general relativity, and he showed what the deflection angle. But Newton was a smart chap, right? So although he thought light was not waves. He didn't, the whole sort of wave nature of light was not understood. He imagined light to be corpuscles, some particles that had mass. And so he said, well, if these guys have mass, then because by my force of gravity, when these light particles come close to another mass, they should get gravitationally focused. They should be attracted. So there would be a deflection in their paths. They wouldn't be going straight anymore. They would get deflected. So he was very clever, and it turns out he calculated what the deflection should be, and it turns out it's only a factor of 2 off from the full general relativistic. So remember, a factor of 2 is a profound change in our conception of gravity, right? And so the deviations, so what we're going to see now are the deviations in the paths of light rays, the stretching and the deflections carry a huge amount of information, both about the shape of space, as well as the masses that are causing the divots that the photons are going to interact with, interfere with on their way to us. So they carry information both about the geometry of the universe as well as the masses that are causing those changes in the geometry. They're both encapsulated in photons, in light, and we'll just see that. And so when Einstein predicted these deflections, and he sort of, his instant fame really came from the fact that, one of the reasons why all of us physicists are so gushy about Einstein and GR is that this was sort of an ex nihilo theory. There weren't a set of, peculiar observations that were in need of an explanation or the need of a theory. This was pure theory. This is as pure as it gets, right? And so then the question is, what can the theory predict Are there observational things that the theory can predict? So people went out and measured. And one of the key predictions was gravitational lensing, this bending of light, because, underlying all of this was a test of this conception of space-time and curvature of space-time due to masses and so on. And so the prediction was that if you went and, Sir Arthur Eddington led a couple of expeditions to go and make this measurement during a total solar eclipse. And so you have the actual positions of stars during a solar eclipse viewed from the Earth. We actually see that there's a difference in the position of these stars. So you can go back 6 months later, see where they really are, and there's a deflection. You can calculate that, and it matched Einstein's prediction. So that is really what made him instantly famous, because this sort of experimental verification of one of the key predictions of general relativity. Okay, so the kinds of objects that I'm interested in are very much more dramatic. And these are basically, if you scale up this idea of a galaxy with a dark matter halo, these are entities, these clusters, that are about 1,000 galaxies that are held together by the gravity of a huge dark matter halo, huge repository of dark matter. And because the masses are so high, the deflections are not as piddly as just moving a star a little bit. They're very, very dramatic. In fact, the effects are so dramatic that if you can think of photons, light, as tubes or rays coming to us, sometimes the deformation is so extreme, the deformation in space-time that the photon has to track, so extreme that one beam gets split into two. And what that means is that you end up seeing 2 images, 3 images, 5 images of the same object, when in reality you have one object. Okay, and I'll show you that. How do we know that? The fingerprint, remember? You can go out and take the spectrum of any image, and the spectra are identical. So there's a very low probability that you would find 2 objects that are in a configuration that is explainable by gravitational lensing that have identical spectra if they are not actually images of the same object. Right? So this is, again, a slightly more sort of a figure that shows you what you can actually measure when you see gravitational deflection. So you have a distant galaxy, and you have light that's coming out of this galaxy, stars in this galaxy, and you have a cluster of galaxies, a huge amount of dark matter. This is space-time. You see a very huge divot here, and you see light that's bent. And so the normal path would have been that. So you can see that it's a very dramatic, this is like the most dramatic bending that you can actually see in the universe. And do we see it? Absolutely. So this is one of the early images of a cluster of galaxies called Abell 2218. And what you see are these distorted shapes. You see all these arcs. So these are distant galaxies that lie beyond the cluster. Notice that the cluster is here in the foreground, and these distant galaxies are what are imaged. And we see everything projected on the sky. So we can't actually tell what is where till we get the spectrum and we know where things are, right? So everything is projected 2-dimensionally on the sky for us. So these arcs that you can pick out by eye, sitting right here, right? These are gravitationally lensed objects. This is a very distant galaxy. It turns out this is actually imaged into 5. I'll just show you some very, very dramatic cases, right? And so you can actually calculate from these deflections, you can actually do the inverse problem, which is to say that you make an assumption from theory of what the dark matter distribution should look like in a region that is a cluster. And then you actually calculate with a given prior distribution of background galaxies what the distortion map should look like. How distorted should these galaxies appear to us? And then you try to match it to this image, and then you back out from that the actual accurate description of the mass. So it's sort of an iterative process, and you try to match it. And to do this, we need exquisite data from, say, the Hubble Space Telescope. You cannot actually do it. The kind of work that I'm going to show you, all the work that I'm going to show you today from my research group needs the highest quality Hubble Space Telescope data and the deepest possible Hubble Space Telescope data as well. Okay, now how this is related to mass, how do we do this inversion problem? How do we back things out about properties of dark matter? So this is a schematic that shows you that if dark matter, right, this halo of dark matter was spherically symmetric, was a nice spherical blob, and you had a source that lines up right behind, then depending on the alignment, I think this laser is gone, unless I'm butterfingered. Okay, I'm butterfingered. Okay, so you have a distant galaxy and you see these deflections. So if things really line up, this individual galaxy could get stretched out into a ring. Okay, and this is seen. These are all real Hubble images. So these are configurations that are actually detected. And if you have a mass distribution that has slightly different symmetry, so if it's ellipsoidal mass distribution, then you could get something. So this is a multiply imaged quasar system. It's called an Einstein cross. So you see actually 5 images of a single quasar. You have something like this. But of course, nature is not simple. So it turns out that the best description for what I just showed you, this image of Abell 2218, is a combination of a lot of clumps of dark matter superposed along with a smooth distribution. Okay, so that looks like the best description for clusters of galaxies. And so, but you might have noticed here that alignment is everything. Things kind of have to line up to give you these most dramatic effects that you can pick out, right? And so depending on exactly where a distant galaxy is behind the cluster, the image will be magnified, distorted, cut into 2, etc. And so location is really, really important. So when there is perfect alignment, you can get something called an Einstein ring. So this is an example of a beautiful, it's an individual galaxy. This is not a cluster. So this is my cartoon galaxy with a big dark matter halo. And this is real data from Hubble image. So a background galaxy which is blue, so it has young stars, it's blue. It has been stretched out to be an almost entire ring. So what has the analysis done? As I said, the process of analysis that people like me do, it has backed out and shown that the lensing galaxy looks like this. This is the light distribution of the galaxy. Obviously, we don't see the dark matter here. This is the light distribution of the galaxy that has a dark matter halo that is doing the lensing. This is the distant source, and this is the distorted image that we see. So this is sort of the surgically cleaned up image that shows you what happened where, right? So now I'm going to show you quickly an animation. So nothing is moving in the universe. This is just to show you the range of configurations that you can likely see when you have a very large cluster with lots of dark matter that's doing the lensing. So you can see these stretched out configurations. I'm just showing you as an animation because now you can pick out by eye when I show you a Hubble image of which kind of configuration, like one long stretchy arc with a lot of little arclets. So just to remind you what's going on here is that we have a uniform sheet of blue circles. Okay, they were all circles. And I've plonked a very massive cluster in front of it. And the cluster is causing the distortions in the shape. So you're seeing a stretching. You see a systematic tangential stretching. And you see these guys that get completely distorted. These are the ones where light beam is splitting, and you're making multiple images, and so on, right? And so what we are looking for in a cluster, so a cluster, depending on how much mass you have, so as I said, a cluster has about 1,000 galaxies, and it has a smooth component. So this is what the smooth component will do. On top of it, individual galaxies in the cluster will have their own little dark matter halos, right? And they will cause a tiny, tiny, tiny systematic distortion on top of this dramatic distortion. And why is this important? This is important because one of the things I'm going to show you is that there is a lot of interesting physics and potential clues to the nature of dark matter in the granularity of dark matter in a cluster, how clumpy it is, how the clumps are distributed. So I'll just go through a couple of Hubble images to show you. So this is a very dramatic one in which you have a galaxy that is shaped like a cartwheel that actually has been imaged 5 times. So you see 4 here, and the 5th image is actually in the center. It's demagnified. These guys are actually magnified. So you see some very, very dramatic effects. So let's come back to this good old cluster, Abell 2218, because I'll try to show you how we have reconstructed the distribution of clumps of dark matter, the entire exquisite detail, the distribution of dark matter. And then I'll show you why that's important. So before I show you that, let me just show you where our theoretical understanding is. Okay, this is a movie that I need to start. Nope. Okay. So what this is showing you, this is not light, it's actually dark matter, just mocked up to look like light so that everyone feels comfortable with the color scheme. So that this is dark matter, and this is the way dark matter evolves, so that what we think constitutes dark matter in the universe are particles that are cold and collisionless, basically slow-moving particles that don't actually collide and actually hit each other. They kind of go past each other. Okay, so and the dark matter distributions that we see in the universe that have driven all the structure formation in the universe, the driving seat of formation of all galaxies, everything we see out there, is that kind of particle best fits the picture. The cold, collisionless dark matter. It's called CDM. And so we find what you're seeing here is a cosmological simulation with that kind of particle that has been followed gravitationally, just gravity go and form the structures. And it forms something that looks like this cluster Abell 2218. And that's the reason I've shown you that movie. And this is a zoom in of a small region of the universe. So just to show you that. So this is again a simulation slice where you can see this is where a cluster would form, where these filaments, I know it looks like neurons, right? So at these nodes, you form clusters. So very massive objects form at the places where these filaments join. So this is a zoom in of a region that would form a cluster later on and produce the lensing. Okay, this is why people like me are obsessed with trying to get at the granularity of dark matter. So these are two simulations with two different sets of properties for dark matter. One of them is the cold dark matter model that I just showed you. We saw the movie. And the other is warm dark matter. And you can visually see that warm dark matter is not as clumpy. Right? And so if you were able to statistically quantify how granular dark matter was by making measurements, then you can actually discriminate between these two possibilities. And remember, I mean, in the absence, as I close, I will show you, in the absence of really knowing what the dark matter particle is, right? We are forced to come up with these sort of indirect tests. And in a way, astrophysics, that's what astrophysics is going to tell us. It's going to be indirect tests always. And it's particle physics that will hopefully help us nail the particle. Okay, so this is the cluster of galaxies. So let me show you really what exactly people like me do. So this is a model for the reconstruction of the gravitational potential of the cluster. And these lines sort of show you what would actually translate to little troughs in space-time. So you're actually seeing the top view. So this is the deepest part. This part is the deepest part of the trough that you would make in space-time. So we're looking down and we are seeing that's where most of the dark matter is lumped. And this is the region where this bunny rabbit region is the region where anytime you have a galaxy behind that yellow bunny rabbit, it will be imaged multiply because there's a huge concentration of dark matter that will split light beams. Okay? And what is shown here is all the Hubble data. These are the shapes of all these galaxies. You take all of this into account and you produce this. Okay? This is the detailed distribution, spatial distribution of dark matter in that region. And so what this shows you is that there's some large-scale component that is smooth. Remember, I schematically showed you that what we understand currently about clusters, and then you have these smaller-scale clumps, and these correspond to individual dark matter halos associated with galaxies in the cluster. So we're able to kind of parse out to see how the dark matter is. So dark matter, it turns out, right, is smeared lightly in the universe everywhere, but there are regions where it's concentrated, and clusters are the regions where it's most concentrated. Okay, so now you can do this exercise. I just want to show you a few plots to show you, it's not just you can do it for one cluster, but we kind of have the data to do it for many, many clusters now. So, and here, this is the one where I showed you the galaxy was imaged 5 times. So, and you can look at the peaks of dark matter here and see that, you know, this region has a high concentration of dark matter, and that corresponds to the region where you have these 5 galaxies. So, okay, so where are we then? So when we can do this analysis, this is one of the, till very recently, this was one of the deepest images taken of the night sky where there was a cluster. And so this is what you see. This is what the Hubble Space Telescope see. This is a multi-wavelength picture. So it's a, you know, many wavelengths were put together to give you this beautiful optical image. And what you don't see, but is there gravitationally, is this blue stuff. This is the reconstruction of the dark matter distribution. Notice it's extended. Notice it traces light. It kind of follows where light is, right? But it's very, very extended, right? And so what's really happened is currently I'm involved in this incredible mapping exercise. It's the deepest look ever taken of clusters by the Hubble Space Telescope, and 6 clusters have been chosen because they are dramatically good lenses. And you may remember I told you that a cluster is going to be a dramatically good lens when things line up, when you have objects right at the right distance behind them, and also when they're really massive, because that's when you get very dramatic distortions, right? So this is a very new result, which we just published last year. So this, as you can see, this image is exquisite. It's just beautiful. You have so many lensed objects that you can, there are more than 100 background sources that are multiply imaged, so there are 300 pieces, right? Things that are imaged multiply. This is the reconstruction of the dark matter distribution in this region of the sky, what you don't see, right? And this is in the blue haze, and the shading of the blue haze tells you where the concentration. So what's very interesting is there appear to be regions. I told you that you roughly follow light, but there are some regions where it appears that you don't see a whole lot of galaxies or light, but you see clumps of dark matter. Okay, so then, as I said, the key is to see if you can discriminate or say something about the particle properties of dark matter by looking at these clump distributions, right? And the dramatic contrasts between cold dark matter and warm dark matter. So it turns out, so this is sort of earlier work in which we looked at the clump distribution is the red histogram, and the black lines that you see are data from the n-body simulation, like the simulation clip that I showed you from that simulation under the assumption that it's cold dark matter. So it actually fits quite well. There's a place where it doesn't look like there's something exciting going on there. So it turns out that is actually 2 clusters that are merging into each other. So you don't actually expect it to fit. So that was then, and now is now. So this is the state-of-the-art simulation, where now our understanding of how galaxies form and everything has really gotten much more sophisticated. So this is very recent data that I have just submitted as a paper, and I just wanted to share to show you how much better our clump distributions have become, and how much better. And what am I after here, right? So what we're really after, right? I'm looking for gaps. I'm looking for a mismatch with the data and the simulation, because that suggests that something in our picture isn't quite right, right? So that's really what one is looking for. So here what we find is, what is interesting is the match is rather good. There's a little bit of an excess of, if you see the red histogram, there's an excess here compared to the curve from simulations. So it turns out that one interesting thing that we have just discovered is that there's something amiss in simulations. There's some physical process that is missing because the simulations are not able to reproduce the radial distribution of where the clumps are. The simulations are a little too diffuse, and the universe seems to be more concentrated. And that could just be that these lensing clusters, right? They're peculiar regions. These are not, these are very special regions. So this is a reconstruction. Notice how much better it's become in terms of the granularity that we can get at. Visually, you can already see that we can find, with this new data set, right, we can do a lot better. So this is where we're at. We have not found a major gap in the theory and the data at the moment. Some suggestive hints that the ways in which we have been studying these simulations, these large computer simulations, are missing some potential ingredients that have to do with the dynamics. So there is something perhaps that the simulations need to be looked at more carefully. So I'm going to now wrap very soon showing you how you can actually get at dark energy as well with the same data set. So essentially, the strength of lensing depends on the mass, as we saw, of the object, as well as the relative, remember I said location, is the relative distance of the source from the lensing mass and us. So it depends on the ratio of those distances. So now consider that you have 2 objects that are lensed by the same cluster. I just told you there are hundreds of galaxies that are lensed by that cluster, right? So if you look at any 2 representative objects lensed by the same cluster, then we can, by looking at constructing the mass model and looking at the strength of lensing, we can figure out what the geometry has to be for light propagation from Z2 to us versus Z1 to us. right? So any change in geometry, so you can actually use them to calibrate, to find out. So if you have lots of multiple images at various distances from the center of a cluster, so these are all behind, these are all objects that are behind, and they could be at various distances away, right? So that's what we're really looking for. Then we can compare the strength of lensing for objects if we know where the objects are, which we do if we have their spectra. And then you can figure out, so really what you're trying to do now is you're calibrating the lens. It's like going to an optometrist, right, and characterizing your glasses. So that's really what we're doing here. So if you do that, if you calibrate the lensing, because if you know what is where, then you get a handle both on the matter distribution and the geometry, because the photons are actually, the light rays are actually traversing various bits of the universe, not identical, but they're sampling different bits of space-time. So you can do that, and it turns out that clusters have been particularly interesting and useful, and so this is a plot that shows you the relative strength of dark energy versus the contents, matter contents of the universe. And the orange banana is the current constraint from the lensing, the clusters that I've shown you. And of course, right, I mean, here the power is in combination of many different independent lines of evidence. And then it's that overlap that gives you the tightest constraint. So zooming in on this orange region, we see that lensing has really helped us on top of the supernovae, on top of other independent techniques to get at dark energy, sort of narrowing the error bars, kind of cornering and sort of trying to define what this dark energy might be. So at the moment, the dark energy appears to be consistent with sort of Einstein's idea of this sort of vacuum energy of space, this lambda, this cosmological constant. Okay, so I want to just wrap up with the uncomfortable situation that we're in, right? So it makes news that we've actually not detected dark matter, and we've been looking for a very, very long time, right? So there's been one experiment, an underground experiment at a mine in Italy, Gran Sasso, that called DAMA, that actually claimed, it's a controversial claim, nobody has been able to replicate, well, they didn't try to replicate. But the new news, I think what is really exciting now is that there is going to be a replication. There are going to be 4 independent experiments that are going to use the same detectors, sodium iodide detectors, put them underground, one in Gran Sasso itself, one in Korea, one in Australia, and one in Spain. And they're going to start taking data in a few months. So in a couple of years, there would be enough statistics to actually see if the kinds of there's an oscillation that you expect when dark matter particles, they're very rare, so they very occasionally go through us. They go through us completely. But if they interact, if you have a sodium iodide crystal, they may jiggle the crystal and generate a little light impulse, and we may be able to detect them. That's the idea, right? And so, and there should be a seasonal variation, because we know the description. We have a description of the dark matter halo, and we can calculate the flux of particles as a function of time. So there should be a seasonal variation with the Earth's orbit around the sun. And that's what DAMA has claimed to have found. And people are now going to replicate it. So, this is, I think, fantastic, because one of the problems with all these expensive experiments has been that nobody wants to do a replication, because, you're not, fame and fortune are not going to be given to you if you replicate. However, it's really, really important, right? And one of the strengths of science is that one has to look for discrepancies, as I started out telling you, that the God is in the gaps, as they say. So why look for gaps, right? So if you look at history and you look at the deviation, there was a deviation in the orbit of Uranus, from Newton's prediction. This is, life a la Newton. And this bright French mathematician, astronomer, Abell predicted that there should be another planet that was actually perturbing everything beyond Uranus, right? And Neptune was discovered. He predicted it, mathematically predicted what the orbit should be for Neptune. They found Neptune. Now it turns out that there was as the data got better, right? So this is when, the data got better, and they noticed that Mercury, there was a bit of a glitch. That didn't fit. And so Urbain Le Verrier said, oh, great, you know what? I think there's another planet between the sun and Mercury, and let's call it Vulcan, and that's what's going on. People looked for Vulcan. A few people found it. Actually, it wasn't found. It wasn't there, right? So it turns out that that gap, right, the gap in understanding, the mismatch in data for Uranus showed you that there was Neptune, but Newton's laws were intact, right, within the same framework. The deviation in the orbit of Mercury actually could be explained only by Einstein's conception of general relativity. The fact that Mercury is closest to the sun and it samples the divot that's produced in space-time by the sun very closely. So there are some aberrations in its orbit, right? And so notice that when you have a mismatch, you can either, a theory needs a little bit of refinement but survives intact, or the entire theory, it's pointing to the existence of an entire new theory. And again, Einstein didn't set out to explain Mercury. It just turned out, right, that his theory managed to. So I think that when we see, so at any rate, at least one of my goals is to see if there are any irreparable cracks that appear in a robust theory, right? Robust cracks. Cracks that persist with many different independent observations. And we know that some of the gaps in our understanding, right, could signal, could give us a clue or a glimpse of another grander, more powerful explanation, a more powerful theory that explains much, much more. So anyway, I will just stop here, and thank you all for your attention. Sorry, thank you. I went over a little bit. Yeah.
So you've linked, there's a certain sort of whew going through the audience here. Keep those questions coming, because otherwise I'm going to die up here. You linked very well dark matter and dark energy in terms of observation, particularly in terms of lensing around galaxy clusters. Is there any linkage, do you think, in them in terms of what they are? Or is it just conspiracy theory says all mysteries are linked, right? So these two mysteries showed up at roughly the same time. We call both of them dark. They must be some two versions of the same thing. Not so.
Yeah, dark is just, phraseology for astronomers when they don't understand something. It's merely that.
Okay.
You don't understand, you just put the prefix dark, and then you feel that, you give it a name and you think you understand, right? No, there have been models. There are models where people are trying really hard to maybe combine the two. Mm-hmm. But there is nothing successful at the moment. That's nothing noteworthy where they are in any way linked. The current description that still survives all the gaps in the test so far is that dark matter are these sort of cold collisionless particles. Mm-hmm. And so the thing is, we really need to get on with it and discover those particles. And I think that I'm really hopeful that if these replication experiments actually see that signal, then we have something. There are other little tantalizing hints from particle physics that it's not clear how they could be related to a dark matter particle at the moment. Mm-hmm. But recently, the LHC, ATLAS and CMS, the two experiments that did find the Higgs, have recently found a sort of a slight signature of a new particle, 750 GeV, that it has the right kind of mass. It could be interesting, either as a dark matter particle itself or be related in some way to what could be a dark matter particle. So what is really seen is sort of a particle that is decaying to give you 2 photons. Mm-hmm. And this is a little bit of an excess there. And so it's a signature of something new that's unexpected. So it's something that was not predicted by any theory, but at the moment can kind of be accommodated. So we need a lot more data to understand it better. Mm-hmm. And first of all, these two experiments don't detect it to the same level of significance. So they need to collect more data, and then maybe there's something there. So I think the clues, honestly, for dark matter are really going to come from the detection of the particle. We really need the particle.
So you think dark matter is likelier to be solved sooner than dark energy in the sense of what gets solved?
Define solve, right?
It's the title of your talk, Priya.
I think that we may have we may have some kind of theoretical, the problem is that whatever explanation you have to come up with, say for dark energy, it kind of has to hang with the rest. A very successful theory that explains a lot of phenomena. So, we need an explanation for dark energy that kind of really hooks in and is consistent with everything else. So it's unclear, how soon that might come.
On the dark energy, which is sort of even more than dark matter, it sounds like fate of the universe story. You mentioned in passing that it's sort of cut in at a certain point after that first 400,000 years. What is known about when and how it cut in?
Right. So one of the key ways, as you can imagine, right? So the dramatic change in expansion history when you start having accelerating expansion is that the sort of distance between pairs of objects is much, much farther away when dark energy starts to kick in. So you can start looking at a signature in the clustering of galaxies, how close galaxies are to each other as a measure of when, and look at how that clustering changes over cosmic time to see when you see the signature. And we do see that now quite clearly. And we can actually figure out that, in the last 5 to 8 billion years is when it actually kicked in. So remember, the time scale of the universe is not a linear time scale, right? So the age of the universe depends on the contents and so on. So it's slightly complicated. So out to redshift, for those of you who sort of read a lot of popular astronomy, so we think it kind of kicks in at a redshift of 2-ish. And we see that signature quite clearly. So we know when it starts to kick in and become important.
So there's an acceleration. Is the rate of acceleration changing, accelerating, decelerating, or is that known?
You mean the next order effect? No, it's not yet. We don't have conclusive measurements, but that's the next step to look at how the acceleration itself changes. So one of the interesting things people are looking for, and that you would, for example, one of the reasons I like clusters is that if that acceleration is changing with time, something like a cluster, you would see it, a very distinct signature in this data. So that's what people are looking at. The moment, there is no evidence for a change, but we'll have to see. I think when the experiments get better and the data gets better.
We'll keep watching for billions of years, hopefully.
Right.
Rich Nauman asks, comment on the possibility that there are different types of dark matter, for example, outside a galaxy, or right there in the center in the plane of the galaxy.
That's a great question. I mean, obviously, it is quite possible that you have different kinds of dark matter, but the simplest possible sort of Occam's razor explanation, you have like one kind, let's try to figure that out, right? So what we do know is that remnants of stars leave little black holes, neutron stars and things, these sort of dark objects that don't actually emit light, they could constitute dark matter in, say, specific places, the center of a galaxy, center of a cluster, a globular cluster or something. So it turns out that when you look at the cosmic inventory and look at all the stars that have formed over the age of the universe and all the little black holes that could have been left over from them and so on, it's not enough to explain all the dark matter that we need to explain the formation of all the galaxies that we see. So you could have other things constitute, a few percent here, a few percent there kind of thing, but it can't be the bulk of dark matter. So we think that the bulk properties, this sort of smeared everywhere kind of dark matter, which is cold dark matter, is probably there's a dominant component. There's room for other things contributing a little bit, but.
There's an interesting kind of historical question. Friedman and Einstein seem to avoid the data realities of their research that implied an expanding universe. So the question is, what are we avoiding today?
We don't have the luxury to avoid data today, right? We are. Yeah.
Can't avoid that one, but the question is, what do we scientists not want to believe in the sense that they didn't? What's just too painful to contemplate? Is there anything you would consider in that category?
I think dark matter and dark energy are pretty embarrassing and painful to contemplate, right? I mean, I think that, if you look at the case that I've been making, right, both dark matter and dark energy are sort of empirically detected, right? So we can't there's no escape from data now. I mean, then that was then, and now is now. So, I mean, we have, and I think what is really powerful, as you said, right? I mean, the reason why a lot of us think this is the golden age of cosmology, it's sort of the interplay of ideas and instruments and data today that's really unique.
So it's more theories than data a while back, and now we got more data than theories that match it. And how will that change? So you've been getting stuff from the Hubble Space Telescope. The James Webb Space Telescope comes on pretty shortly. How will that affect your and everybody else's astrophysics?
Right. I mean, I think with every new telescope...
say a little about the Webb telescope and how it's different.
So the James Webb Telescope has these filters, basically the eyes through which it's looking at the universe. It's more sort of the infrared, which is the longer wavelengths, the redder wavelengths. And these are the wavelengths in which when you have stars, new stars that form, there's a lot of dust around them. This is the radiation, this is the re-radiated stuff. So the blue stuff is absorbed and it's emitted redward. So you see a lot more of the dynamical stuff that's happening, the reprocessing that's happening in the universe, dust in the universe, will be revealed by JWST. So it's almost like opening a new set of windows into the universe. And if you see, so for example, the cluster of galaxies that I just showed you, I showed you all these optical images. If you go and look at that same region with an X-ray telescope that picks up the most energetic photons, which are in the X-ray, short wavelength, you find that it looks very diffuse because there's a huge amount of hot gas that is sitting in that gravitational potential that you don't see in the Hubble image at all, and you see it only in the X-ray. So the idea is that when we create a model, then we have to reconcile all these different ingredients and views of the object. So JW is going to be really, really important in our understanding of like the first stars that formed that are probably extincted a lot by dust. Therefore, the radiation would be re-radiated in the infrared wavelengths. And so I think it's going to open the new window into the first stars and the first galaxies and the first black holes.
Say more about you haven't talked much about black holes tonight. I know that's part of your study. What do you hope to get from the James Webb Telescope in your black hole work?
So, I have been working, in terms of black holes, I've been working most recently on the formation of the first black holes, and in particular, a new way to form them, which is to form them to be very massive from the get-go. So you basically have large lumps of gas that become gravitationally unstable, then coalesce and form a very massive black hole to start with. The normal picture is that you form the first black hole when the first star exhausts all its fuel and leaves a remnant. And that's a very tiny little black hole. And that, it turns out, is not enough to explain the quasars that you see in the universe. And as you look further and further out, you're seeing these quasars, very bright quasars that are powered by extremely supermassive black holes in place when the universe was just 1 billion years old. So how did that happen? You don't actually have enough time to grow a piddly little hole to that mass. So you have to make a more massive black hole from the get-go. So that's a model that me and my students and postdocs have been working on for many years. And that makes very distinct predictions on the total number of very massive growing black holes that will glow in the infrared that should be seen by JWST. So I'm very, very excited about what the James Webb Space Telescope will uncover. Very nervous about how it has to all open up in space, right? Especially because recently we lost this incredible satellite that I was very hopeful about for black holes. Hitomi, the Japanese satellite, it disintegrated after being successfully launched. So without giving us data. So the material you've published on black holes makes specific predictions for what the data will show from the James Webb? What the spectrum should look like for those objects and how you would identify them and so on. It's very exciting, really, really exciting.
So you'll be either right or wrong or further puzzled.
Well, when I started doing this work on trying to compare with, cold dark matter models, I was quite young, right? This was 10, 12 years ago, and I thought, I'm going to become really famous. I'm going to find something that doesn't match. I'm going to find a crisis, right? I didn't. I mean, it all kind of fits, right? I mean, which is kind of good. So we don't have to completely throw out the theory, but it would have been nice, right?
But Susan asks, so. Everything begins with so in this part of the world. Does dark matter and dark energy hint anything about multiple universes? And the multiverse, is that impinge on your domain or not?
No, but I have beliefs. But
Belief.
I use that word very, very consciously.
Okay.
I mean, I like the idea of a multiverse because, I kind of alluded to this a little bit by saying, our universe can be described with with a set of 6 numbers that kind of, a few of them appear in those Friedman equations. So you go out and you measure them, and you just need 6 numbers to describe the past, present, future of the universe. And if some of these numbers were slightly different from what we measure them to be, we wouldn't be here, we wouldn't have had this we wouldn't have had this particular cosmic drama unfold the way it did, right? And so why these 6 numbers? And to me, it seems like a convenient out, and I'm admitting it's a convenient out, to just say that there could be other universes out there with different combinations of 6 numbers, different values that would have different ingredients, different geometries, and different expansion histories and so on. And so I'm happy to accommodate the belief that we could have a multiverse with many other instantiations of. So the reason it's a belief is that at the moment, it is hard to see how, just by how we've constructed our theories, right? So the cosmic speed limit is the speed of light. And so the observable universe is a finite limit, and then we can't see beyond it, and any other bubble universe is somewhere beyond our reach. So by construction, we can't get evidence the way we normally think about in science, observational evidence and so on for this hypothesis, right? And so it's a belief. But then, I am open, because can you imagine, I don't think Copernicus would have thought, even though he did an amazing thing, he moved the pivot from the Earth, to the sun. I don't think he could have imagined that we would have landed on the moon. It was beyond the realm or the scope of imagination for him, right? And so, I'm open to the idea that maybe there will be breakthroughs that will somehow, there are already some calculations that suggest that maybe these bubble universes could have collided and you could have some tremor that you might see in the CMB. There's no, the data is not good enough. There's nothing that suggested that that's a fruitful explanation at the moment. But, who knows? A few hundred years from now, if we haven't destroyed our planet and we're still here, and, maybe we'll find something different that might be evidence for the multiverse.
Well, there's sure a lot of people who counting on it in one level or another. The science fiction writers, a fair number of physicists. And, if the multiverse turns out not to be the case, that by now would almost be a surprise for people. Here's a question from Anonymous asking, how does a collisionless particle get detected in the experiments you mentioned in Spain and so on?
That's a great question. It just kind of passes through. And so you kind of have to wait for it. I know. And remember when the opening thing...
But if it passes through and is collisionless, how do you know that happened?
No, it jiggles a crystal or whatever. So
it jiggles a crystal, just by its mass, okay.
Yeah, but it's mass, right? It's passing through, and it sort of changes the crystal structure. And you can, we have instruments that will then convert that into a light impulse if it goes through. And of course, you have to worry very carefully about everything else that can jiggle the cluster,
exactly.
the crystal, right? But, I don't know, I'm very hopeful, right? I mean, look at LIGO. I mean, their detection was just incredible. So...
Of the gravity waves.
Yeah, that they could characterize all other effects that could mimic the real thing extremely well, right? Because it was a precision measurement, right? The strain was 10 to the minus 21. I mean, it was really quite something. So, I mean, I think the dark matter experiments the sensitivities are not, quite there yet. But, people are building bigger and bigger vats with bigger crystals, bigger detectors. See, one of the problems with the dark matter is that so we are groping in the space. So what we're really looking for is the parameter space is the mass of the particle and the interaction cross-section. It's a weak interaction cross-section. So there are swaths of the space that we know are ruled out if we believe in the current theoretical ideas. If we think that, we've kind of really understood the particle content of the universe, and the standard model is right, we can kind of rule out regions. But the available parameter space is still vast enough that we kind of don't, there's room. There's still a lot of room. And so we have detectors that are looking in particular ranges. again, guided by what we think, the epoch at which this dark matter particle could have formed in the early universe, therefore the kind of mass range, the kind of mass range that would conveniently solve the dark matter problem, right? I mean, in a way. So this is literally, a drunk looking for keys under the...
Right.
So that sort of thing. It's not that bad, but it's kind of close. It's kind of close.
Well, it sounds like these keys are evenly distributed, so
A lot of keys.
the right
There's a
place
lot
to
of
look
keys.
is under the light.
Yeah.
But it also sounds like they're pretty rare if you're waiting a long time for one to go by your crystal.
Yeah.
This is very dilute, this dark
Right.
matter.
I know, given where we are in the solar system, right? The question is, as I said, dark matter is smeared lightly everywhere in the universe, and there are places where it's lumped. We actually happen to be in the location away from the center of our galaxy at a place where the dark matter density is actually quite low. So it's our location as well that folds into this.
You described the halo of dark matter around these galaxies. It's very thin out there, but it adds up to a lot because there's so much
There's a lot in
perimeter.
the center, so it's heaped in the center, and so there's a very particular functional form for how the density of dark matter scales as a function of radius from the center of a galaxy. So there's a nice peak, it's kind of heaped in the center, and then it kind of falls off as we go out.
But out to some distance.
Yeah,
farther
out to
than the
quite a
stars.
large distance, but it kind of really oozes, and it sort of really merges with what is cosmically smeared everywhere.
Would we be better off as dark matter detectors if we were in a galaxy cluster of some consequence?
Sure, maybe, yeah, maybe. But, I think that, but we're not. So.
And that is so hard to fix. Say a little more about the difference between the warm dark matter and cold dark matter. That one kind of went by quick. And it sounds like your findings are going in the direction of cold dark matter and clumpiness. Are there opposing theories that have other things to say?
Well, so in terms of, so one thing that I did not mention, right, and there was a reason I didn't mention is that, the people tried the sort of the historical story with which I closed about trying to change the theory versus amend the theory slightly. So one kind of alternative to dark matter that has been proposed is a modification of Newtonian dynamics. But this has not been successful. And in fact, it was very exciting because it was kind of successful. So they changed the force law and they changed how that falls off, if you will. Vaguely, that's sort of what they did. And that is Bekenstein, Milgram and Bekenstein, two scientists in Israel. And it turns out that they could kind of explain away the need for dark matter on the scales of galaxies. They could kind of say, well, it's really the modification of gravity. But the place where the whole thing falls apart is that kind of theory, which has no dark matter, cannot explain the light bending. No matter how sophisticated they make it, they have not been able to bend light. And it's on the scale of clusters that the whole thing falls apart. And that's why I like clusters, because they've already discriminated and ruled out so one set of... So the thing about therefore, there are actually, as I said, there are a few gaps. So one of the gaps that is there in the current cold dark matter model is that the inner regions of galaxies, the expectation of how dark matter should be, the expectation is it should be a very peaky distribution. And it appears in a lot of galaxies, in particular the low luminosity galaxies, that the dark matter distribution that you infer from the data is actually like a core, like a smooth smear in the center. Sort of, it's like having a nice little peak that's been smoothed out. And so one explanation for that is that you have a slightly different kind of dark matter particle, a dark matter particle whose mass is such that it sort of free streams and it doesn't clump on very small scales. There's a characteristic scale below which it doesn't actually clump. And that's why the distributions are so much more smoother than that of cold dark matter model. So it turns out that, again, you can use the warm dark matter, you can invoke it and say, well, I can kind of explain away the centers. But then when we try to tie that to the amount of dark matter that we need and all the other observations, right? There's a characteristic scale that should show up the dark matter initially is as you have these fluctuations in the dark matter density of little heaps and little troughs, and then they amplify over time. And that's why you get that network that you see, right? So it turns out that the warm dark matter would actually then, you wouldn't see a lot of those networks, and we actually see them. So, so that, particle, again, I think there's room for that kind of particle being a small contributor to the whole sort of dark matter bucket, right? So you have this other thing, and then you have some other small pieces like little black holes, maybe some little bit of smattering of warm dark matter. So there are constraints on how much that could be. But it cannot be the entire inventory of dark matter that we infer.
There you go.
These particles.
Just to connect this to pop culture for a minute, there was a movie recently that took black holes very seriously.
Oh, that's not relevant to dark matter, but it's relevant to black holes, and it's one of my favorite recent movies, Interstellar. And sort of what I really liked about that movie...
How many here saw Interstellar?
Almost everyone,
Okay,
yeah.
so...
I mean, this is San Francisco. You must have all seen it, yeah. It was awesome. The visual effects were fabulous, right? So what was interesting to me about the movie, and I sort of wrote a very gushy review of it, was that the calculations of light bending by this huge black hole called Gargantua, that those equations were actually Einstein's equations that were solved for light bending. So they actually did the computation. And they also had, and so they had Kip Thorne, who's one of the sort of leading minds in terms of understanding black holes. He was a co-producer in that movie. So I think his job was to make sure that no laws of physics were violated when this movie was made, but that he was willing to kind of extrapolate just a little bit beyond what is known, right? And so for me, the coolest thing about that movie, other than the visualizations and the black holes and stuff, is the fact that a scientific paper emerged from the making of that movie in that visualization, a peer-reviewed paper. How often has Hollywood collaborated with Kip Thorne?
So how did these movie makers wind up co-authoring a scientific paper? What did they do that was new?
So they actually calculated the paths of light rays around the black hole, and because they had heavy-duty computational equipment, they found there was some interesting nonlinear effects that hadn't been noticed before. And Kip wrote that up. And
Hollywood had stronger computers than Caltech, is that what happened?
That particular, yes, that visualizing, I think it's called, the place was called Double Negative. I forget what they were called, I'm blanking out now. But that company, yes. But they are incentivized to do these calculations, possibly, right? The movie, I think, minted money. It just was so popular everywhere.
In case there's any questions lingering on how art and science can intersect, this is one. And you got lots of science coming. I hope there's artists paying attention. This is going to be great. We're going to have fun this century. Thanks a lot.
Thank you so much.